Hi there, welcome to Labster. In this simulation, you will learn about orbits and Kepler's laws. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Perfect, then let's get started with your first mission. Our mission today is to find out if there is life in the planetary system of the Ostakos star. Click on the screen in front of you to search for planets orbiting Ostakos. Click on the screen in front of you. On this screen, you can see the position of the planets orbiting Ostakos as black dots. We want to identify their orbits, so we can see if any of them is fit for life. Like in every solar system, the planets travel in elliptical orbits with their star in one focus. This is known as Kepler's first law, or law of the ellipses. Use the sliders on the screen to match the ellipse to the orbit of the planets. You can adjust the semimajor axis of the orbit, its longest axis, with the horizontal slider, and the semi-minor axis, its shortest axis, with the vertical slider. Once the ellipse you draw matches the orbit of a planet, we will get a preliminary report on its habitability. Is there anything else you'd like to know before experimenting with elliptical orbits? You can check out the Theory tab on your lab pad at any time to learn more about orbits and ellipses. Match the ellipse to the different orbits. The ellipse will turn green as you approach the orbit of a planet fit for life. You have found the orbit of Ostakos 3. Temperatures are mild enough for life on this planet, but my spectrometers detect no signs of water in its atmosphere. It is unlikely that it harbors life. Its orbit is near the warmest edge of the habitable zone. The orbit of a planet fit for life should be around this size or bigger. You have found the orbit of Ostakos 2. During most of its year, it is too close to its star for life to survive in it. Its orbit is also very squashed. It is unlikely that we will find any other orbit with such a high eccentricity. You have found the orbit of Ostakos 1. It is too close to its star, so it is unlikely that we find life here. A planet fit for life should have a much bigger orbit. Click on the lab. You have found the orbit of Ostakos 4. This orbit is pretty eccentric, so the distance of Ostakos 4 to its star varies considerably through its year, but it remains within the habitable zone. This means that there could be liquid water on its surface all year long. My spectrometers show that its atmosphere is very similar to Earth's too. We should definitely take a closer look. Congratulations! You have found all orbits of the Ostakos star system. What did the orbits of all planets in the Ostakos system have in common? Spot on! The orbits of Ostakos planets are elliptical and they have their star in one focus. This is known as Kepler's first law, and it is true in every star system, including ours. Ostakos 4 is a perfect candidate to continue our search for life. Let's get closer to have a better look. Pull the lever to approach Ostakos 4. We are now approaching the orbit of Ostakos 4. To study the planet closely, we must stay right by it as it moves and, for that, we need to know how fast it is moving at each moment. Otherwise, we'll be left behind. Kepler's second law can help us understand how a planet moves in its orbit. Notice that Ostakos 4 sweeps each of the pizza-shaped sections of its orbit in the same amount of time. Some of these sections are long and narrow, and some are short and wide, but they all have the same area. Kepler's second law, or law of areas, is just that. Planets sweep equal areas of their orbits in equal intervals of time. Taking Kepler's second law into account, where in its orbit is Astrakos 4 moving fastest? Exactly. When Astrakos 4 is closer to its star, the section it sweeps is shorter, so if all sections have the same area, the arc it travels in a given time must be longer to compensate. This is how Kepler's second law helps us understand how a planet moves in its orbit. Well done! Now that we know how the planet moves, we can follow it closely. Look! We are now right in front of Astrakos 4. Could those large blue areas on its surface be oceans? How very lucky! It looks like we could really find life. We should send some satellite probes to investigate further. To have better control over our satellite probes, we must understand how objects move in different orbits. Astrakos 4 has 2 moons, Aphros and Bythos, each in an orbit of a different size. The orbits of these moons have a very low eccentricity, so we can approximate them by circles. Observing the orbits of Astrakos 4's moons will give us the first hint on how the motion of a satellite relates to the size of its orbit. Which of Astrakos' moons is moving faster? That's right, objects on smaller orbits move faster. Because the orbits of Astrakos' moons are, in good approximation, circular, comparing their radii is the best way to compare their sizes. Satellites in smaller orbits seem faster, but by how much? Let's find out by sending some satellite probes and measuring how long it takes them to complete one orbit around the planet, or, as scientists say, their orbital period. We will collect some data on the periods of different orbits. I've set the velocity of the probe to create an orbit with a radius of 30,000 kilometers. Select the radius of the orbit with the slider and observe how long it takes the satellite probe to complete one orbit. Our data will appear on the graphs on the lateral screens. Use the slider to select an orbit of 30,000 kilometers and pull the lever to send the probe. Look, we have the data from our first satellite probe. It is on the screen on your left. Click on the screen on your left. We set the radius to 30,000 kilometers and got an orbital period of 0.61 days. Look now at the screen on your right. I have also plotted the square of the orbital period against the cube of the radius. Why, you ask? No particular reason, of course. I'm sure this won't come up later. Anyway, let's get more data. I've set the velocity of the probe to create an orbit with a radius of 50,000 kilometers. Select the radius of the orbit with the slider and observe how long it takes the satellite probe to complete one orbit. Our data will appear on the graphs on the lateral screens. Use the slider to select an orbit of 50,000 kilometers and pull the lever to send the probe. I've set the velocity of the probe to create an orbit with a radius of 90,000 kilometers. Select the radius of the orbit with the slider and observe how long it takes the satellite probe to complete one orbit. Our data will appear on the graphs on the lateral screens. Use the slider to select an orbit of 90,000 kilometers and pull the lever to send the probe. Fantastic! I have found the curves that best fit our data and plotted them on our graphs. Check the graphs carefully to answer the following quiz question. What is the relationship between the radius of a circular orbit and its period? That's right. The ratio between the cube of the radius and the square of the period is always the same for any object that orbits * 4. This relationship is known as Kepler's third law, or law of harmonies, and it applies to the moons and satellites of any planet and to the planets of any star. The ratio between t² and the cube of ar changes for every system of orbiting bodies, but it is always the same for every object within the same system. Even though we have only studied circular orbits, Kepler's third law applies to any elliptical orbit, changing the radius to the semimajor axis. I'll write the equation of Kepler's third law on the middle screen so we can always have it at hand. Now, let's apply what we have just learned. There is an area of this planet that looks particularly interesting. It is a lake on the equator that could be a comfortable habitat for many species. We should take a picture. To take a good picture, our satellite should always remain over the lake. That means that our satellite should orbit * 4 at the same rate that * 4 spins on its axis. On Earth, that kind of satellite is called geostationary. * 4 stationary doesn't roll off the tongue as nicely, I'm afraid. Conveniently, a day in * 4 and Earth lasts the same. Both planets spin on their axes at the same rate. Using this information and Kepler's third law, choose the right radius for our * 4 stationary orbit. You will need pen and paper for this task. If you don't have a calculator at hand, you can use the one on the top right corner of the lab pad. Choose the right orbit for a satellite that stays over the same point on * 4 surface. Well done! Kepler's third law relates the periods of orbits with different radii, so we can use it to find out the radius of an orbit if we want it to have a particular period. Now, let's see the picture our satellite took. Oh my, could those be trees? There definitely are complex forms of life on this planet. I can't wait to explore more. Maybe we could even establish a human colony. Thanks to your knowledge of orbital motion, we were able to explore the Ostaco system and find life in one of its planets. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.